In this video, we introduce an approach for preference-guided, multi-objective optimization for UI adaptation. Optimization-based UI adaptation has proven to significantly improve usability of interfaces, particularly for mixed reality applications. Commonly, adaptive interfaces are achieved by framing UI adaptation as a multi-objective optimization problem. This approach typically results in a set of Pareto optimal designs, where each design excels in some objectives while sacrificing performance in others. However, this method has two key limitations that hinder its ability to fully adapt to the diverse needs and preferences of users. The first limitation is that it is unclear which final design to select from the Pareto frontier. One common approach is to transform the multi-objective optimization problem into a single objective problem by weighted sum. However, this leads to information loss, since not all Pareto optimal solutions can be reached when exploring solutions via manipulating weights. Recent work allows users to explore multiple Pareto optimal designs. However, this manual exploration requires users to engage with a multitude of UI layout candidates, which is both time-consuming and cognitively demanding. The second limitation is that the Pareto frontier search in previous works is evenly distributed across the objective space and does not account for user preferences. This issue is particularly significant because it could mean that the region of user-preferred designs is not sufficiently explored. We propose a new optimization approach for UI adaptation that guides Pareto searches by user preference. Imagine a user in a coffee shop wearing their mixed reality device. When the user moves the virtual music player next to their phone, our approach infers a preference for semantic alignment between virtual widgets, like the music player, and physical objects, like the phone. It then optimizes the layout to maintain this alignment, positioning the video viewer and news page near the iPad, while placing the Messenger, Instagram, and music player closer to the phone. Our approach starts with the user adjusting a UI element of an initial layout. We use the changes in objective function values from these movements to derive the user's preference ranking across the optimization objectives. Our approach then employs these rankings to categorize individual objectives into distinct priority groups. Using a lexicographic, multi-objective optimization method, we guide the search along the Pareto frontier, aligning the exploration with the user's preferences. Our approach then identifies the optimal layout by using the user's adjustments as a reference point and selecting the nearest candidate on the updated Pareto front. This selected candidate defines the complete UI layout. The process iterates with each UI adjustment until the user is satisfied with the final design. We demonstrated our approach within a 3D mixed reality context, but our method can equally be applied to 2D interfaces. To evaluate its effectiveness and efficiency, we conducted a user study to compare it against two baselines, manually adjusting the elements of an initial Pareto optimal layout and selecting the Pareto optimal layout closest to the manually adjusted UI element positions. Results showed that our approach significantly reduced the need for manual UI adjustments while maintaining high user satisfaction with the final design. It further reduced the distance between moved UI elements and the nearest Pareto front candidate for high-priority objectives, showing that inferring user preference rankings and optimizing accordingly brought the Pareto front closer to preferred layouts. This is evident when comparing the objective space generated by a previous method to that of our approach. With each iteration of our algorithm, the Pareto front shifts towards regions in the objective space that reflect the user's preferred layouts, ensuring that optimized layouts better align with user preferences. The user is dissatisfied with the initial UI layout and creates space to move the PDF viewer to the center of their view, closer to the tablet. From this movement, our approach detects a preference for central alignment and semantic agreement. The optimized layout respects these preferences by shifting UI elements toward the center and aligning widgets that are semantically related to the phone or the headphones.